Warning: Earth's magnetic weak spot is growing. The satellite began to reboot, then failed. Alarms rolled across the control room as instruments spiked. Gyros drifted, and the spacecraft started to tumble over the South Atlantic. In orbit, astronauts watched silent lightning, brief flashes behind closed eyes, each a high-energy particle slicing through the retina. On the ground, pilots logged radio hiss mid-ocean. Engineers circled a patch on the map where glitches cluster. I have a name for it. The South Atlantic Anomaly, Earth's magnetic weak spot, is growing and splitting into two lobes. It means more radiation for crews and electronics, more faults in low orbits, and a question: why is our shield thinning here? Roadmap: what will prove and how? Here's the plan. First, we're going to validate the weak spot with data, not vibes. We'll show how modern satellites, Swarm, Champ, and Orsted, map the depressed magnetic field stretching from South America to Southern Africa, and how the 2025 ESA Swarm updates confirm the anomaly's expansion and westward drift at roughly 20 kilometers per year. We'll underline a key twist. The anomaly now shows two intensity minima, a western lobe over South America and a deepening eastern lobe southwest of Africa. Then we'll drop beneath our feet. We'll go to the outer core where liquid iron flows, because that's where Earth's magnetic field is generated. We'll explain why the tidy bar magnet analogy breaks in a messy convecting planet, and how localized reverse flux patches at the Core-Mantle boundary can thin the field above, seeding regions like the SAA. Next, we'll follow consequences. Human first. Spacecraft logbooks, single event upsets, bit flips, detectors saturated over the SAA. ISS crews reporting phosphene flashes during nightly passes. Why hardened birds survive and CubeSats struggle. Then aviation exposure, wildlife navigation, and why ground level risk stays low for now. We'll widen the lens to the fading dipole, the global field's decline since the 184s, and what paleomagnetic archives say about reversals and excursions. We'll separate evidence from speculation. Weakening does not guarantee a flip, and outline realistic timelines. Finally, we'll land on what to watch and what to do. Better mapping cadence, SAA, aware mission planning, grid and airline playbooks, and public literacy to retire apocalypse myths. To understand the whole, we start with the shield we can't see how Earth's magnetic field works. Stand at night on a polar runway and feel the air crackle. Above you, space weather is trying to reach the ground. Most of it doesn't, because Earth runs a hidden engine. Deep below continents and oceans, roughly 3,000 kilometers down, the outer core churns. It's liquid iron alloy, electrically conducting, hot and moving. Motion of conductor through magnetic field induces current. Current generates magnetic field. That feedback loop is the Geodynamo. It runs without batteries, powered by heat leaking from the core and the slow crystallization of the inner core. We like to picture a bar magnet. It's a decent first sketch. A dipole with field lines arcing from one polar cap through space and back into the other. But the real field is layered and lumpy. The dipole is the backbone, yes, but superimposed are multipoles, quadrupole, octopole, and finer harmonics born of turbulent flow. This matters because the bar magnet picture can't explain regional dents like the South Atlantic Anomaly. Multipoles can. From the surface up, field lines swell outward to form the magnetosphere, the comet-shaped bubble that diverts most solar wind. On the day side, pressure pushes the magnetopause inward. On the night side, it stretches into a tail that can snap and fling charged particles toward us. Inside that bubble sit the Van Allen belts, donuts of trapped protons and electrons spiraling along field lines. Normally, those belts hover high, but where the surface field is weaker, the inner belt dips closer. That's the SAA problem in one sentence. Thin the field locally, and the particle population comes down to meet you. Low Earth orbit satellites that skim a few hundred kilometers up suddenly fly through denser fluxes of high-energy particles. When a proton plows into a memory cell or detector, it can flip a bit, scramble a packet, or seed a cascade of errors. Spacecraft designers fight this with shielding, error correction, and safe modes. The Hubble team powers down sensitive instruments during SAA transits. The International Space Station crosses 3 to 4 times a day. Crews ride through it like sailors crossing rough water, sometimes seeing those phosphene sparks with eyes closed as particles graze their retinas. But let's not jump ahead. Why is the field uneven at all? Because the core is not uniform. Heat flux varies across the core-mantle boundary. Think hotter patches where the lower mantle pulls heat, cooler elsewhere. Plumes and jets of liquid iron twist, shear, and reconnect magnetic structures. In some places at the top of the core, tiny regions of reversed magnetization, reverse flux patches appear. They're not full flips, but they oppose the main dipole locally, weakening it. Over thousands of kilometers above, that shows up as a broad intensity low. Dipole versus multipoles is also why the field evolves. The global dipole has been declining since the 184s, but not smoothly. Regional features wax and wane, drift west at tens of kilometers per year, and split or merge. In 2025, the Swarm constellation mapped the SAA's western minimum near South America and a deepening eastern minimum southwest of Africa. That split matters operationally: a wider hazard zone, different fault statistics, and more complexity for mission planners. Field lines aren't just geometry, they're rails for particles. Along these rails, charged particles mirror between hemispheres. Where the field weakens, their mirror points sink. That's why detectors see higher count rates over the SAA. Meanwhile, at high latitudes, open field lines funnel solar particles into the atmosphere, painting auroras and sometimes unsettling power grids. The same shield that saves us from constant radiation also couples space to ground in storms. Where is the field strongest? Near the polar caps, if you measure vertical component, near magnetic anomalies of continental crust if you measure at small scales. Where is it weakest? Today, broadly across the South Atlantic and Southern Africa, the SAA footprint. Regional anomalies aren't rare. What's unusual here is the size, the depth, and the trend. What about people on the ground? At sea level, the atmosphere remains an excellent shield. Primary cosmic rays collide high above, creating showers of secondaries that we live with daily. The SAA doesn't erase the air, but it shifts risk in the sky and in orbit. Airline routes that linger near the South Atlantic pick up small, trackable dose increments. Satellites eat more glitches. Electronics age faster. The field is a moving target. It's built by fluid motion, altered by mantle structure, and modulated by the sun. There's no on-off switch, only a living map that updates in fits and starts. The bar magnet was never broken. It was never the whole story. The South Atlantic Anomaly, the hole in the shield. Draw a line from Recife to Namibia and out into open water. Under that arc, the compass doesn't quit, but the numbers sag. Satellites feel it first. The South Atlantic Anomaly is where Earth's magnetic intensity dips lower than anywhere else at similar latitudes. A broad depression stretching from South America across the southern Atlantic towards southern Africa. It isn't a hole in the sense of empty space. It's a thinning, just enough to let the inner Van Allen belt droop closer to low Earth orbit, where hardware and humans actually live. We didn't guess this into being, we mapped it. The first global fingerprints came from missions like Orsted and Champ. Then the European Space Agency's Swarm constellation took over the Long Watch. Year after year, Swarm stitched together a time-lapse of the field's surface strength. The pattern is unmistakable. The anomaly has grown in area, deepened in intensity, and drifted westward. In 2025, Swarm updates pinned that drift at roughly 20 kilometers per year and confirmed a split into two lows. One entrenched over South America, another steepening southwest of Africa. Operationally, that's two potholes in the highway instead of one. What does weaker look like from orbit? It looks like dosimeters ticking faster and detectors peppered with spurious flashes. Over the SAA, the inner radiation belt's high-energy protons ride field lines down until their mirror points sink to a few hundred kilometers. A satellite that would normally skim beneath the worst of the belts instead plows straight through the densest particle soup of its day. Hubble switches off delicate cameras. Space stations cross 3 or 4 times daily, crews noting those phosphene sparks blinking behind eyelids. It isn't science fiction, it's logged as routine. Zoom out and you see structure inside the dent. The western minimum, the deeper of the two, sits over South America. The eastern minimum, a newer feature to the southwest of Africa, has been dropping faster. Models that blend Swarm with China's CSES and Macau's MSS1 agree on the two-lobe shape and assign it different rhythms. The western lobe creeps along with modest intensity change. The eastern one steepens more rapidly without much east-to-west motion. That asymmetry hints at what's happening below. Under the South Atlantic, at the top of the core, the magnetic field isn't smooth. Small regions of reverse polarity, reverse flux patches, interrupt the main dipole. They're like eddies on a river that locally push water backward while the whole flow still runs downstream. Stack enough of those eddies and the net push weakens overhead. The lithosphere and its lower mantle complicate the picture by channeling heat unevenly. Where the mantle draws more heat, core flow patterns change, sculpting those patches and nudging them west. The SAA's migration follows. Weak spot doesn't mean no shield. At flight levels, the atmosphere remains a robust radiation sink. Airline crews crossing the South Atlantic accumulate small dose increments comparable to other long routes, tracked and regulated. Birds don't fall out of the sky, but navigation is a different story. Creatures that sense magnetic inclination and intensity, sea turtles, migratory birds, experience a landscape whose contours drift over lifetimes. There's active research here, and the results are subtle. Not catastrophe, but stress on systems tuned to a quieter map. On the ground, compasses still point. The anomaly's real bite is in space operations. Single event upsets, bit flips caused by one energetic particle, cluster over this footprint. Sometimes they're harmless. A checksum trips, a processor resets, a file is corrupted and retransmitted. Sometimes a chain of faults cascades into a safe mode entry at the worst moment. Designers harden against this with error-correcting memory, watchdog timers, voting logic, shielding, and annealing cycles that heal damaged detector pixels. They also plan routes through the sky, like pilots plan fuel stops, timing observations to avoid SAA passes, accepting downtime as the price of orbit. The question that keeps coming back is movement. Why west? Because the geomagnetic field's secular variation includes a persistent westward drift of non-dipole features, likely tied to planetary scale waves in the core. The SAA rides that conveyor. Why two lobes now? Because whatever is reorganizing the core top field beneath southern Africa, which sits above a peculiar deep mantle domain, has strengthened the eastern reverse flux. That doesn't announce an imminent flip. It announces complexity. Watch the sea level of magnetism, and you'll miss the weather. The SAA deepens by tens to hundreds of nanoteslas over years, but storms can spike radiation on top of that in hours. When the sun launches a coronal mass ejection, the belts swell and deform, and the anomaly's effect is amplified. That coupling, internal field shaping the stage, external forcing driving the play, is why operators treat the SAA as a constant hazard with variable mood. So the map changes, and we change with it. Agencies publish updated models, World Magnetic Model for navigation, high-resolution variants for mission design. Swarm keeps flying, the SAA keeps migrating, and each year, the quiet dent in our shield writes itself a little deeper into spaceflight standard procedures. Beneath the anomaly, core flow and reverse flux patches. To understand why the shield thins over the South Atlantic, we have to look where the field is made. Not at the surface, but at the top of the outer core, a 3,000-kilometer deep ocean of liquid iron alloys sliding beneath the mantle. The Geodynamo isn't a rigid bar. It's a restless factory where flow sculpts magnetism. And like any factory, bottlenecks and backflows show up as defects in the final product. Start with heat. The core loses energy upward, but the mantle doesn't pull evenly. Beneath southern Africa and the South Atlantic sits one of Earth's great deep anomalies, a region of unusually hot, dense mantle known to seismologists as a large, low shear velocity province. That patchwork in the mantle changes how heat leaves the core. Where the mantle extracts heat more efficiently, the core cools faster. Where it insulates, heat lingers. Flow follows those gradients. Jets, gyres, and helical plumes of metal shift, twist field bundles, and stitch together patches of magnetism with different polarity and strength. At the core mantle boundary, those tangled flows can generate small areas where the radial magnetic field points the wrong way relative to the global dipole. Geophysicists call them reverse flux patches. They aren't reversals of the whole planet, more like eddies in a river that momentarily push upstream. Stack a few eddies side by side, keep them marching in the same direction, and the main current slows. From space, that looks like a broad intensity low, the South Atlantic Anomaly. How do we know patches exist where we can't go? We infer them from secular variation, the year-to-year change in the field measured by satellites and ground observatories. Think of the field as a movie. If you can see how the image shifts frame to frame, you can reconstruct where the projector is wobbling. Inversions of Swarm, CHAMP, and Orsted data produce maps of core top magnetic features. And the same motifs keep appearing: strong flux concentrations under the Pacific and Asia, and a cluster of reversed or weakened flux beneath southern Africa that drifts westward. The SAA rides on top of that conveyor. That drift matters. Non-dipole field features tend to slide west at tens of kilometers per year, a signal of planetary scale waves in the core, quasi-geostrophic gyres and torsional oscillations that sweep magnetism along. The SAA's westward crawl mirrors the motion of the reverse flux beneath it. The two-lobe structure Swarm flagged in 2025, the entrenched western minimum over South America and the faster deepening eastern minimum southwest of Africa, fits this picture. It suggests a mature patch downstream and a re-energized patch upstream, both fed by the same flow regime. There's a second fingerprint at work: growth and decay. Reverse patches don't just travel, they wax and wane as flow reconfigures. Faster cooling in one core sector can sharpen shear, which strengthens local field generation of the opposite sign. Slower cooling elsewhere relaxes it. Over years to decades, you see that as a deepening or shallowing of the surface intensity. Low. Over centuries, archaeomagnetic records, pots fired in the Iron Age, lavas from historic eruptions, hint that this dance has played out before in southern Africa. A sharp regional dip between the 13th and 16th centuries, then partial recovery. Weak patches can be recurring behavior, not a one-way slide into reversal. Meanwhile, the mantle's role is not passive. The deep African anomaly alters how buoyancy plumes rise in the core, steering flow paths. Picture a ceiling with warmer and cooler tiles, convection rolls organized beneath the pattern. Numerical dynamos that impose core-mantle heat flux heterogeneity produce long-lived non-dipole features beneath southern Africa and the South Atlantic, and a field depression at the surface with westward migration. All SAA hallmarks. The modeler's lesson is blunt. The core writes the script, but the mantle edits. A skeptic might ask, if patches oppose the dipole locally, why doesn't the whole field flip? Because reversals need the dipole to fail globally. Most of the time, the main axial dipole remains strong enough to dominate, and patches are just noise on top. In weakened epochs, that balance can tip into excursions. Brief, partial collapses of the dipole with wild directions, but even then, recovery is common. Today's global dipole has declined since the 184s, yet paleofield statistics and modern synthesis studies argue a flip is not inevitable or imminent. The SAA is a regional dent with deep roots, not a countdown clock. What about the split lobe asymmetry? Beneath southern Africa, core top reconstructions show clustered flux of opposite sign, sitting next to robust same sign concentrations. Flow shear between them can amplify the reverse patch. Downstream, as the patch smears and weakens, the surface imprint persists but shallows. That gives you a steeper eastern minimum and a broader western one, exactly what Swarm and companion missions have mapped. Tie that to torsional waves, cylindrical oscillations in the core that move angular momentum outward and inward on decadal scales. And you have a mechanism for the staggered deepening rates. Every so often, the system surprises. Rapid jerks, abrupt changes in secular variation, show up in observatory records and satellite fits. Those are likely signatures of flow accelerations at the core top, perhaps linked to buoyancy pulses or magnetic instabilities. When a jerk propagates through the South Atlantic sector, the surface anomaly's contours shift a little faster, and satellite fault maps notice months later. The factory hiccuped, the product changed. Pull back, and the story is coherent. Uneven heat loss across the core-mantle boundary scopes core flow. Core flow organizes patches of magnetism that sometimes oppose the dipole. Planetary scale waves push those patches west. The mantle's deep structure over southern Africa helps anchor and shape them. And the sum projects upward as a thinning of the field over the South Atlantic that splits, drifts, and breathes. No mystery portal, no doomsday script, just a restless engine and a shield that wears its workings on failure logs and design workarounds. Open a mission log and you can trace the South Atlantic Anomaly in handwriting. It shows up as resets at odd minutes, as corrupted frames flagged by checksums, as gyros that briefly don't agree with themselves. The Hubble Space Telescope learned early to schedule around it. When the orbit carries Hubble over the SAA, delicate instruments are powered down, shutters close, and the telescope rides out the pass. On the International Space Station, the anomaly is a daily ritual. 3 to 4 crossings every 24 hours. Crews sometimes note phosphene flashes, tiny sparks behind closed eyelids as energetic particles slice through retinal tissue. The station keeps working. People adapt, the logbook remembers. Stakes first. A single proton does not care about a billion-dollar mission. If it plows through a memory cell, it can flip a bit. That's a single event upset, an SEU. If it deposits enough charge in a sensitive junction, it can latch a transistor on until power is cycled. Single event latch-up. If it strikes a detector, it appears as a bright pixel or a streak. None of these are mysterious. They're physics showing up in silicon. Over the SAA, where the inner radiation belt dips closer, the rate climbs. A camera designed to count galaxies suddenly counts high-energy snow. A computer that has run for months without a hiccup reboots twice in one orbit. Action. Ground controllers plan around the footprint. Hubble's teams post SAA avoidance zones, blocking science during those windows. The Fermi Gamma Ray Space Telescope flags the region in its data pipeline. So spurious triggers don't masquerade as astrophysics. CubeSats and small missions with thinner budgets and lighter shielding take the hits hardest. One university satellite rode through a cluster of SEUs, then a latch-up that tripped a power rail. Only a watchdog timer and a cold reboot brought it back. Another survived by annealing, warming detector arrays on command to heal radiation damage and reset hot pixels after repeated SAA transits. Some failures are quiet. A magnetometer saturates. A star tracker loses the field when cosmic rays pepper its sensor, so the spacecraft switches to gyros and drifts a fraction before reacquiring. Some are loud. A flight computer resets and the craft drops into safe mode mid-observation. On a good day, the system recovers after one orbit. On a bad day, thermal limits move, fuel is spent reorienting, and an entire observing campaign slips. This is where design earns its keep. Hardened electronics resist bit flips, but they cost mass and money, so operators layer defenses. Error-correcting codes catch single-bit errors and vote them down. Triple modular redundancy runs 3 copies of critical software and accepts the majority opinion. Watchdog timers reboot subsystems if they hang. Current, limiting, and crowbar circuits cut power fast during latch-up. Shielding, aluminum tantalum, adds grams to intercept lower energy particles. None of it makes the SAA go away. It makes the anomaly survivable. Mission planning changes too. Low Earth orbit constellations pick altitudes and inclinations with the SAA in mind. If your life depends on precise pointing, you schedule maneuvers and calibrations outside the worst flux windows. If you're a surveyor, you accept the noise and filter it later. Some teams move to higher or lower orbits to dodge the densest slice of the belt. Others go to cislunar space. James Webb's perch at L2 is outside the anomaly's reach. For those who must stay low, autonomy matters. Spacecraft learn to detect their own radiation environment, switch to robust modes on entry, and resume full operations on exit without phoning home. Human bodies are detectors too. On station, crew exposures track pass by pass. Dosimeters ride on walls and suit pockets. Procedures route spacewalks away from SAA crossings when possible. The flashes in the dark are reminders, not emergencies. Medical teams watch long-term totals. Engineers watch component lifetimes. The SAA's bite is cumulative. Impact ripples beyond individual missions. Insurance models price SAA risk into premiums for commercial satellites. Procurement specs now call out single event immunity levels. Launch providers brief customers on the anomaly during rideshare manifest meetings. Even radio operators who never leave the ground notice, as satellites flying through the SAA drop links or glitch transponders for a few minutes over the South Atlantic corridor. Meanwhile, new tools sharpen the map. High-resolution magnetic models update the boundaries yearly. Space weather dashboards integrate swarm data, radiation belt models, and solar wind readings to forecast flux enhancements on top of the baseline dent. During storms, operators widen margins, longer avoidance windows, more aggressive safe mode entries, because the belts swell and the SAA's effect amplifies. There's craft in the workarounds. A. A small Earth imaging satellite overflew the anomaly during a geomagnetic storm. Star trackers speckled, attitude control wobbled, and the flight computer saw a cascade of errors. A ground team watching the pass watched their momentum wheels saturate. The satellite auto-safed just as designed, then 2 orbits later, woke, reacquired stars, and resumed imaging over Namibia. The next day, engineers pushed an update that narrowed the tracker's acceptance window over the SAA and increased gyro blending. A week later, the same storm pattern brought the same pass. The logbook shows only a line, transit nominal. None of this is glamorous, it's competence. Hardware hardened enough, software skeptical enough, operations humble enough to leave slack in a schedule the sky can steal. The anomaly deepens and splits, the procedures do too. Designers draw maps with moving potholes, crews ride the rough water, and every time a satellite wakes cleanly on the far side, the SAA is just one more line on a well-kept list. Radiation, flights, and biology, who gets exposed? Stakes first. Up where the air is thin and the metal is light, radiation stops being background and becomes a design constraint. The South Atlantic Anomaly doesn't turn planes into spacecraft, but it nudges dose up where crews already live closer to cosmic weather. The question is who notices, how much, and what changes on the ground because of it. Action. Airline routes crossing the South Atlantic, Sao Paulo to Johannesburg, Buenos Aires to Cape Town, long hauls that curve through the mid-latitudes, spend hours in air that even outside the anomaly carries higher cosmic ray flux than sea level. Add the SAA's thinning field and you pull more secondary particles into flight levels during disturbed periods. Pilots hear it as a note in a briefing. Medical officers see it as cumulative dose logged in millisieverts per year. Regulators already track this. In most jurisdictions, flight crews are classified as radiation workers. Airlines model routes, altitudes, and solar cycle to budget exposure. Impact. How big is the bump? On typical mid-latitude flights, dose is dominated by galactic cosmic rays and rises with altitude and latitude. Over the SAA corridor, the increment is modest in quiet space weather and grows when radiation belts swell during storms. Operators respond with altitude changes or slight route shifts on high-activity days. It's the same playbook used for polar routes threaded through auroral zones. Trade a little fuel for a little less flux. For passengers, the dose remains small against medical imaging or terrestrial background. For crews flying week after week, the ledger matters. Meanwhile, balloon and high-altitude measurements fill in the vertical. Radiosonde gondolas and research balloons launched out of Brazil and Namibia ride through the anomaly's footprint, counting muons and electrons in the stratosphere. The profile shows what the models predict. A subtle enhancement layered onto the usual cascade of secondaries from cosmic rays. It isn't a beam. It's a slightly thicker drizzle in a narrow band of longitudes, louder during solar storms. Quieter at solar maximum when the sun's wind actually shields Earth from some galactic cosmic rays. On orbit, biology notices more directly. Astronauts report phosphene flashes, streaks of light with eyes closed during SAA passes. That's a particle traversing retinal tissue, not a metaphor. Medical teams track individual exposures with dosimeters on the station walls and on crew vests. They schedule spacewalks away from anomaly crossings when possible and budget cumulative totals across missions. Even so, long-term health risk management rests on statistics and prudence. The line between acceptable and excessive is guarded by time limits, shielding, and trajectory choices. Wildlife? It's tempting to draw a straight line from a magnetic weak spot to confuse migrations. The reality is subtler. Many species key on the magnetic field's inclination and intensity to help build mental maps. Birds, sea turtles, even some fish. The SAA doesn't erase those cues. It shifts the contours over years. A hatchling in Brazil imprints on a magnetic signature near a beach. A decade later, that signature has drifted west a touch, and adults aim slightly off unless they refresh with other cues. Stars, smell, coastline. Field studies find stressors and detours, not collapse. Magnetoreception is a braided sense. Animals rarely lean on one strand alone. Ground truth matters. At sea level across the South Atlantic footprint, the atmosphere's 12 kilometers of air remain the dominant shield. Dosimeters in coastal cities don't jump when satellites scream. Hospitals don't see a radiation spike on SAA days. If risk moves, it moves aloft, air routes, and orbits. There's a quiet operational consequence for airlines beyond dose. Communications and navigation have moods over the anomaly. HF radio can hiss. Satellite links that pass through spacecraft crossing the SAA may momentarily degrade. Dispatchers learn the pattern the way a farmer learns a wind. Expect a little friction over this patch. Keep an alternate channel ready, log, and move on. In the worst space weather, carriers delay or reroute, just as they do on polar tracks. Meanwhile, research keeps tightening the bounds. Aviation authorities ingest real-time space weather feeds, solar wind, geomagnetic indices, radiation belt models, and post advisories. Airlines fold those into flight planning software that already juggles turbulence and jets. Wildlife biologists tag birds and turtles with sensors that record both position and local field, building maps of how magnetosensory species adapt as the anomaly drifts. Balloon campaigns sample altitude bands. Few planes occupy, pinning down where enhancement matters and where it doesn't. Microstory. A captain flying Recife to Johannesburg watches the ops note. Elevate by 2,000 feet between 30 west and 10 east. KP high. Expect HF flutter. They climb, burn a little more fuel, ride smoother air, and log the segment. In the cabin, nothing feels different. In the crawl space above the ceiling, a passive dosimeter adds a tiny line to a long record. Bottom line. The SAA's biological footprint isn't a thriller. It's a planning problem. Space crews get tracked and shielded. Aircraft tweak routes on rough days, and animals that read the field adjust to a map that moves underfoot. The shield is thinning locally, not failing. Knowing where and when turns worry into procedures. The fading dipole. Are we heading for a reversal? To see where the South Atlantic Anomaly might be heading, zoom out to the whole shield. Observatories have watched Earth's dipole strength slide since the 184s, roughly a 5% drop per century in direct records, with hints of earlier decline in archaeomagnetic data. That number fuels late-night headlines about an imminent flip. The story that actually fits the evidence is slower, messier, and less cinematic. Weakening is real, reversal is not guaranteed, and regional dents like the SAA can grow without the planet turning its polarity inside out. Stakes first. The dipole is the backbone that holds the belts high and sets the baseline for space weather. When it weakens, regional anomalies get room to breathe. The SAA deepens and broadens, bringing the inner belt's particles closer to low Earth orbit more often. That's why satellite fault rates creep up over the Atlantic. But a weaker dipole does not mean no shield. It means a different map. Lower intensity in some sectors, slightly higher in others, and more work for mission planners. Action. What do past flips tell us? Rock archives, the Brunas, Matoyama reversal, 780,000 years ago. The last Champ excursion, 41,000 years ago, show that polarity changes do happen. They also show how they happen. Patchy, region by region, with global dipole strength dropping, multipoles taking over the field, and the compass going weird for centuries to millennia before settling. Even excursions that didn't complete the flip brought dramatic local swings, then recovery. No one saw days to weeks catastrophe. No one saw the field vanish. It reconfigured. Impact. So where are we now on that spectrum? Modern syntheses that stitch observatories, satellites, and archaeomagnetism together argue we are not in an early phase of a reversal or excursion. The dipole is declining, the fall is not monotonic, and the present configuration, with the pronounced South Atlantic low and strong flux patches elsewhere, fits a mode the Geodynamo visits without flipping. The field's history is littered with erratic slopes, plateaus, and rebounds. Weak epochs can recover. Meanwhile, models let us study what if. Feed realistic core flows and core-mantle heat flux patterns into numerical dynamos, then dial down the dipole. A consistent picture emerges. As the backbone softens, non-dipole features grow teeth. The SAA intensifies and sprawls, lobes split and merge, and westward drift continues. Satellites in low Earth orbit see higher dose rates and more frequent single-event upsets. Aviation dose budgets inch up over specific corridors during storms. Grids feel sharper storm time currents in vulnerable regions. None of that requires a flip. It requires a dipole trending down. Uncertainty is part of the deal. The Geodynamo is turbulent. Core flow changes on decadal scales, jerks, can accelerate or decelerate the decline locally. Mantle structure steers where patches grow. Solar cycle modulates space weather on top. That makes prediction a cone, not a line. Timelines for a true reversal, if one were brewing, are measured in centuries to millennia. Signals you'd expect first: a deeper global dipole minimum, non-dipole energy overtaking the dipole, and widespread rapid directional swings recorded across the globe. We're not seeing that package. A skeptic might ask about the modern decline slope. It looks steep compared with simple diffusion. True, but past centuries held comparable rates in reconstructed data, and they flattened. The lesson from archaeomagnetism is humility. The field's short-term tempo misleads about its long-term destination. The lesson from paleomagnetism is patience. Flips happen, but the clock is irregular. What if the dipole keeps slipping for the next few generations? Then the near-term story is planning. Space agencies harden electronics, schedule around bigger SAA footprints, and use radiation-quiet orbits where they can. Airlines bake space weather into ops on South Atlantic corridors, the way they already do on polar routes. Grid operators in Southern Africa and South America invest in monitoring and storm time procedures that assume slightly lower margins. Navigation models update yearly. Public literacy catches up. Weaker does not equal absent. Flips do not come overnight. Storms still matter more than background on any given day. There's another meaning hiding here. A living shield breathes. It's built by a fluid engine. It carries memory and surprises. It's sensitive to the mantle it slides beneath. That's why the South Atlantic looks the way it does, why the eastern lobe deepens faster, and why history shows repeat dents in the same sector centuries apart. The dipole's decline gives those patterns leverage, but early reversal is a claim the data don't earn. So, are we heading for a flip? Not on a human timescale you can schedule against? Are we heading for a world where the SAA is a bigger, trickier pothole and storms hit a little harder where the field is soft? Yes. That's enough to keep engineers busy. Transition. Even without a flip, the near term matters. The shield's slow fade makes the SAA's consequences louder, and the coupling between space and ground during storms sharper. Grids and airlines are already adjusting. Now we need to show how. Tech on the line, power grids, pipelines, and storm coupling. Stakes first. Electricity is confidence. Lights that stay on, signals that arrive, pumps that run. When the shield thins over the South Atlantic, storms have a little more reach. Not drama every day, but higher odds that the next bad solar eruption pushes deeper currents into wires on land. Operators in Southern Africa and South America know this in their bones. The question is how a dent in the sky turns into stress in copper and steel. Action. Start with the chain. A coronal mass ejection hits. The magnetosphere compresses and rives. Over the SAA, where intensity is already low, the geomagnetic field changes faster for a given solar shove. Faster change means larger induced electric fields in the ground. Those fields drive geomagnetically induced currents, GICs, up transformer neutrals and along long conductors. It isn't voltage that cooks a transformer, it's quasi-direct current that saturates its core. When that happens, waveforms distort, reactive power soars, protection relays chatter, and the grid starts to run out of margin. Impact. Southern Africa's backbone makes this personal. A north-south high-voltage corridor laces Namibia, Botswana, and South Africa. Transformers along that path have seen jits on storm days. Small, measurable steps in neutral current that line up with magnetometer spikes. Substations near the SAA's margin feel it sooner. In Brazil and Argentina, east-west lines that hug the southern latitude band cross-crust with complicated conductivity. Basins, shields, coastlines, so induced fields pool unevenly. One storm makes city lights dim in Porto Alegre while a neighboring province cruises. It isn't fairness, it's geology. Meanwhile, pipelines become antennas. Steel tubes that run hundreds of kilometers across Patagonia or the Karoo sit under the same electric fields. Companies run cathodic protection to stop corrosion, imposing a gentle countercurrent that keeps metal from dissolving into soil. Storm time GICs ride on top, swinging potentials by volts. The coating picks up the difference. Any tiny flaw turns into a battery and starts chewing steel. The damage hides until a survey months later finds a spot where the pipe wall thinned a hair too far. What nobody knew at the time, the first time, was how local it feels. A storm that barely nudges a transformer in Ghana can trip alarms in northern Chile. The SAA doesn't flip a switch, it lowers thresholds. Add storm time belts swollen over the anomaly, and you raise the chance that satellites feeding grid timing drop packets right when operators want clean phaser data. Two nuisances line up and become a night shift. Microstory. In a Johannesburg control room, a supervisor watches reactive reserves slide during a KP7 storm. A transformer on a coastal line hums hotter, neutral current climbs. The team opens a shunt reactor to prop voltage, redispatches a generator inland, and phones a neighbor to trim transfers. A protection relay trips on harmonics. They reclose after. A check. By dawn, the magnetometer's calm. The memo the next day: add GIC monitors to 2 more substations, advance an oil test, and widen storm procedures by 1 notch. Mitigation is craft and map. You can't move the sun or the SAA, but you can change how conductors invite trouble. Series capacitors block quasi-direct current on long lines. Transformers with higher saturation margins forgive more. Neutral blocking devices add friction to GICs at key nodes. Grounding schemes shift current away from sensitive cores. Windings chosen for lower harmonic susceptibility by breathing room. None of it is free. All of it beats waiting. Operators run playbooks. Space weather alerts ripple from observatories into grid control centers. When the forecast says strong, dispatch shifts. Reduce flows on vulnerable corridors. Hold more reactive power. Postpone maintenance that narrows topology. And raise staffing. Automatic controls get conservative. Under-frequency load-shedding thresholds adjusted a hair. Special protection schemes armed. Practice matters. Drills turn alerts into reflex. Pipelines adapt too. Controllers watch close-interval surveys more often after storms. They log pipe-to-soil potentials in real time and temper cathodic protection rectifiers to avoid overcorrection swings. When a storm spikes, crews patrol known coding holidays. Weeks later, they dig to verify the wall. The best day is boring. A spike on a chart and a note that the coding held. What about communities? Telecom backhaul rides the same poles and ducts. Storm time harmonics can foul repeaters. Water systems depend on pumps. If a feeder trips and backup lags, reservoirs dip. Small industries notice first: arc furnaces that quench on flicker, process controls that reboot on sag. Space weather sounds far until the plant manager is on the phone with the utility asking if the flicker is done yet. The SAA's growth tightens this weave. As the anomaly deepens and splits, the footprint of elevated risk spreads west and east. That doesn't guarantee disaster. It guarantees more nights where a storm forecast triggers an extra checklist. It nudges capital planning. More monitors this year, 1 more blocking device next, an earlier transformer replacement in a hot corridor the year after. Engines and shields share a rule: margins matter. A thinner field over the South Atlantic lowers margin. Good engineering puts it back. That's the quiet victory. Lights that never blink, pipelines that never leak, a control room shift that goes home on time with nothing to tell their family. Stakes first. When a map of the sky starts carrying potholes that move, the people who live in that sky change their routes. Airlines and space agencies already have a playbook for the South Atlantic Anomaly. It's not fear, it's choreography. Dose budgets, safe modes, anneal cycles, and a growing respect for a dent that won't sit still. Action. In dispatch rooms from Sao Paulo to Johannesburg, the SAA is a line on the briefing. Flight planning software ingests base weather dashboards, radiation belt models, geomagnetic indices, swarm-informed magnetic maps, and suggests minor altitude tweaks across the corridor on active days. Crews are radiation workers by regulation. Company medical teams track millisieverts per year and smooth schedules, so the same people don't stack long segments during a bad solar week. On rare storm days, they treat the South Atlantic like the poles. Climb 2,000 feet, shift 100 nautical miles, trade a little fuel for quieter air. Airlines also hedge communications. HF circuits can hiss in disturbed conditions. Long-haul captains file alternates for data link and SATCOM. Dispatchers pre-brief the hiccup. Expect scratchy HF between 30 west and 10 east. Use secondary frequencies. Log and continue. Maintenance rides along in the margins. Avionics health monitoring flags any soft resets that cluster over the anomaly. If a box shows a pattern, technicians pull it at the next hub because radiation aging isn't dramatic, just steady. Meanwhile, satellite operators fly a stricter dance. Mission control rooms place SAA boxes on every timeline. Hubble's instruments go dark on entry and wake on exit. Fermi marks its triggers suspect inside the footprint. Earth observers accept striping and schedule anneals, warm-up detectors to heal pixels after clusters of passes. Constellations like imaging fleets bake SAA cadence into duty cycles. Duty high over Africa and Europe, idle over the South Atlantic, resume over South America. Ground teams automate this reflex, so a storm window at 2 in the morning doesn't need a phone call. CubeSat teams adapt with humility. Thin shielding and tiny budgets mean more upsets, so they write software like they expect errors. Watchdogs reboot subsystems cleanly. Triple modular redundancy votes down bad bits. If a latch-up trips a rail, a current limiter cuts power, waits, and brings the board back without human hands. The best small missions aren't brave, they're skeptical. Space agencies move pieces you can't see. Navigation models update yearly. World magnetic model for aircraft. Higher resolution variants for flight dynamics. Operators upload refined SAA polygons to onboard tables, so satellites self-gate instruments in the right minutes. Radiation belts aren't static. Swarm's 2025 map added a faster, deepening eastern lobe, so planners widen blackout zones for orbits crossing southwest of Africa. Procurement follows. Contracts now specify single-event immunity levels and anneal support. Insurance noticed. Underwriters price SAA risk into premiums for low Earth orbit payloads that spend a lot of time in the corridor. Operators answer with data. Fault rates per orbit, latch-up statistics, recovery timetables. The cheapest policy is competence in a binder. Microstory. An Earth science satellite heads into commissioning. On day 3, a star tracker loses the field over the anomaly. The software blends gyros too slowly, the vehicle drifts, the camera safes. The team pushes a patch that narrows the tracker's acceptance window over SAA coordinates and increases gyro weighting during entries. Next pass, the tracker stays quiet through the snow, the satellite points. The line in the logbook shrinks from a paragraph to SAA transit nominal. Human spaceflight adds a heartbeat. Station planners sequence spacewalks away from SAA passes when they can, shuffle crew sleep on storm weeks, and load personal dosimeters into pockets. The flashes in the dark are a note, not a siren. Medical teams watch totals. Program managers watch lifetime margins on gyros and avionics that age faster when radiation is noisy. There's also a quiet exodus. Missions that can leave low Earth orbit do. James Webb sits at L2, far from the anomaly's reach. Deep space probes cruise where the SAA is just a footnote in a training class. For those who must stay low, Earth watchers, weather fleets, internet constellations, the answer is density of craft and depth of procedure. Lose one to an unrecoverable latch-up and the network reroutes. Lose a minute over the South Atlantic and the ground pipeline fills the gap from neighbors. Culture shifts with maps. 10 years ago, the SAA was a quirk on a slide. Today, it's a column in budgets, an annex in ops manuals, and a color on every mission planner's screen. The anomaly deepens and splits. The playbook learns new steps. The goal isn't to beat the dent, it's to make it boring. The evidence board, satellites, observatories, and lava rocks. Lay the cards on the table. First card, satellites. Orsted and Champ started the global map 2 decades ago. Then ESA Swarm took the long watch, 3 craft flying in formation, slicing Earth's field into vector components day after day. Stitch those passes into time-lapse, and the South Atlantic Depression doesn't just sit there, it evolves. You see the aerial expansion, the westward crawl, and by 2025, 2 distinct minima, a western crater over South America and a deepening eastern dip southwest of Africa. Independent work that folds in China's CSES and Macau's MSS1 resolves the same 2-lobe shape and assigns different tempos. The western lobe creeping, the eastern dropping faster. Different sensors, same picture. Second card, radiation monitors. It's one thing to measure field intensity. It's another to count particles where hardware lives. On the International Space Station, passive dosimeters and active counters log dose rates orbit by orbit. Over the anomaly, the counts tick higher, reliably. Hubble's detector teams plot hot pixels against longitude and get a South Atlantic bright patch every time. CubeSat missions carry simple Geiger tubes and see the same bump. Balloon campaigns launched from Brazil and Namibia push instruments into the stratosphere and catch a subtle enhancement layered onto the usual shower of secondaries. Not a beam, not a scare story, just a measurable uptick that lines up with the magnetic map. Third card, ground observatories. The quiet backbone is a global ring of magnetometers that measure field strength and direction at fixed points year over year. Stations ringing South America and Southern Africa register a persistent intensity, low relative to peers at similar latitudes, and, crucially, secular variation that matches the satellite movie. When the swarm fits, say, westward drift at roughly 20 kilometers per year, the ground curves bend the same way. During storms, those observatories record sharper d/dt in the anomaly's neighborhood, the fast changes that matter to grids. Space and ground aren't two stories. They're the same signal seen from above and below. Fourth card, lava and clay. Archaeomagnetism takes you places satellites can't go, back in time. Iron minerals in fired pottery and baked hearths lock in the field direction, and strength when they cooled. In southern Africa, Iron Age sites preserve a sharp regional dip between the 1300s and the 1500s. The same sector that's weak today was weak 600 years ago. Paleomagnetism adds volcanic flows. A Cape Verde sequence carries cooling ages and remnant intensities that, when combined with global models, show the dipole and its regional anomalies waxing and waning across the last millennium. It's not a perfect archive. It has smudges and gaps, but the motifs repeat. Southern Africa is a recurring troublemaker. Fifth card, models that actually respect physics. Inversions that combine swarm vectors with ground data reconstruct core-top flux. Under Southern Africa, they keep finding reversed or weakened patches drifting west. Numerical dynamos that impose mantle heat flux heterogeneity, like the deep African anomaly, produce a surface intensity low in the South Atlantic sector, and that familiar westward tread. These aren't cartoons tuned to fit one map. They're engines that generate a whole field, then get judged against many constraints at once. If a model that matches high-latitude secular variation also spits out an SAAI-like depression with two minima, you start to trust the storyline. Core flow plus mantle structure can make this dent and make it drift. What ties the board together are cross-checks. Satellite map minima coincide with peaks in spacecraft fault logs. Ground secular variation matches the drift in space. Lava records confirm that this corner of the planet has seen deep local lows before, then partial recovery. A new eastern minimum deepens faster in 2025 data. Core top reconstructions show reverse flux intensifying upstream beneath southern Africa. None of these cards alone proves inevitability. Together, they argue recurrence and mechanism. We also pin the limits. At sea level, dosimetry across the footprint stays steady. The atmosphere is still king. Aviation increments remain modest and manageable outside storm weeks. The anomaly's bite is mainly in low orbit and in storm coupling. And reversals? The lava card that tempts headlines, the Lachamp excursion, shows wild swings that recovered. The dipole's long slide since the 1840s earns attention, not a countdown. That's how you read an evidence board without scaring yourself into fiction. You rank signals by coherence. Satellites say, 2 lobes, westward drift deepening. Monitors say higher counts here. Observatories say, same motion on the ground. Rocks say, we've done versions of this before. Models say, the core and mantle can make. The conclusion is boring and powerful. The SAA is real, evolving, and explainable. And that makes it actionable. Myths versus reality. What a flip would and wouldn't do. Let's clear the fog. A geomagnetic reversal isn't a movie cut to black. The field doesn't vanish. It weakens, gets messy, and the multipoles take over while the dipole shrinks and wanders. Compasses point weird directions, sometimes toward the equator, sometimes in loops you wouldn't trust to find a door. But the magnetosphere persists. It sags, it rattles, and it lets more radiation into near-Earth space. Yet the shield still works. Myth 1. A flip means mass extinction. Reality. The geologic record doesn't show synchronized die-offs lined up with reversals. Life rode out the Brunas, Matuyama reversal 780,000 years ago, and the Lashamp excursion 41,000 years ago. There were regional climate effects and auroras at strange latitudes, but no planet-wide biological collapse tied to magnetism alone. The atmosphere remains the dominant radiation barrier at the surface. Myth 2. It happens overnight. Reality. Centuries to millennia. Reversals unfold in fits and starts. Regional patches flipping back and forth, dipole strength sagging, then recovering into the opposite polarity. Even fast excursions like Lashamp lasted on the order of centuries for the dramatic parts. That's long enough for societies to adapt infrastructure if they know what to expect. Myth 3. GPS and satellites die for good. Reality. They suffer, and engineers compensate. During a weak multipolar interval, the radiation environment in low Earth orbit gets harsher, fault rates climb. So spacecraft use heavier shielding, smarter error correction, more aggressive safe modes, and, when budgets allow, orbits that spend less time in the belts. GNSS accuracy may degrade in disturbed conditions, but dual frequency receivers, augmentation systems, and alternative navigation, celestial fixes, terrain maps, inertial, fill gaps. Redundancy is the business model. Myth 4. Power grids collapse globally. Reality. Storm risk rises. Blackout probability clusters regionally. Mitigation works. Lower field strength in some sectors means stronger ground electric fields for the same solar push. That's a bigger bite for Southern Africa and South America, the SAA neighborhood, and other vulnerable grids. But operators can reduce flows on long lines during storms, add series capacitors and neutral blocking devices, harden transformers, and practice storm procedures. It's a planning problem, not an inevitability. So what does a flip actually do? It moves hazard maps. Satellite lifetimes shorten unless costs rise. Spacewalk timelines get fuzzier. Aviation dose budgets require more careful routing on bad solar weeks. Mid-latitude auroras become a sometimes thing. Radio propagation over long paths gets moody more often. Navigation models that assume a strong axial dipole lose accuracy. Higher resolution, frequently updated maps become standard. The SAA-style dents don't disappear. They multiply and migrate as the field reconfigures. Meanwhile, everyday life at sea level remains mostly unchanged. Your phone still orients if the software knows the local field. Your refrigerator doesn't care. The biggest visible differences show up during storms. More spectacular skies, more frequent warnings for grids, more caution in the upper air. And the timeline gives us slack. We won't wake to a flipped world. We'll watch maps drift for generations. There's one more myth worth killing. Weakening guarantees a flip. It doesn't. The field has slipped before and recovered without crossing zero. Today's decline since the 1840s is notable, not prophetic. What's robust is the near term, a deeper South Atlantic anomaly, higher radiation in low Earth orbit, and sharper storm coupling where the field is thin. Treat those as certainties to manage, not omens to fear. Bottom line, a reversal is a stress test, not an apocalypse. The shield changes shape, the atmosphere still guards the surface. The magnetosphere still stands, if lower and noisier. The risks we can't dodge, we can budget. Harden satellites, update models, drill grids, plan aviation routes with space weather on the dashboard, retire the disaster script and keep the competence. The field will do what fluid cores do. Our job is to be as adaptive as the planet that made it. What to watch. Early warnings and practical moves. If you want to know where this goes next, watch the needles that move before headlines do. Start with salinity and winter mixing in the three basins that matter most: the Labrador Sea, the Erminger Sea, and the Nordic Seas. When surface freshening thickens the lid, winter storms don't punch as deep. Profiling floats that can survive polar nights already sample those layers. A trend towards shallower mixed layers and trapped subsurface heat is a quiet alarm. Pair that with deep water formation proxies. After a storm, the ocean should show a clear reset. Oxygen and heat buried to depth as the column overturns. Fewer of those deep resets, or smaller ones, means the engine is losing stamina. It won't make the nightly news, but it's a lever mission planners, airlines, and grid operators can pull against. Next, gradients. The Gulf Stream's sea surface height and density slope is a mechanical tell. Flatten it, and you've softened the overturning's push. Tide gauges along the U.S. East Coast record that in clustered sea level bumps, altimeters from orbit see the slope itself. Watch for seasons where coastal sea level sits high more often without a storm in sight. That's the background easing, not a freak tide. A newer physics-based metric sits farther south, the freshwater import and export across the Atlantic's southern boundary. In models that tip, that budget approaches a minimum before flipping sign. Routine ship sections and drifters can estimate it well enough to track a direction of travel. If the curve keeps bending toward that minimum, you widen margins across the board. Early warning statistics close the loop. Systems that approach a tipping point wobble longer and wider when you poke them, critical slowing down. Apply that math to independent fingerprints, the subpolar temperature, salinity contrast, the dipole minus non-dipole energy ratio, even carefully filtered SAA depth indices. If autocorrelation and variance rise together across several series, you don't declare doom, you declare the runway shorter. None of this is a spectator sport. Practical moves start with instruments. Expand the winter-capable Argo array in the subpolar North Atlantic. Anchor more moorings across key latitudes, not just at 26.5 degrees north, with real-time telemetry. Fold China's CSES and partner missions into open data streams so modelers can sharpen core top inversions and SAA maps faster, and give coastal tide gauges better vertical control so subsidence doesn't masquerade as dynamics. Policy is a second instrument. Regulators can nudge airlines to embed space weather and routine dispatch the way turbulence already is. Require annual radiation dashboards that fold in solar cycle and route exposure for crews, and fund small reroute allowances during active weeks. So safety isn't a line item casualty. For grids in Southern Africa and South America, tie storm hardening incentives to specific diagnostics. Neutral blocking at vulnerable substations, series capacitors on long lines, transformer procurement that raises saturation margins, and permanent JIC monitors feeding regional situational awareness. Satellites need budgets for boredom. Pay for error-correcting memory, latch-up protection, anneal heaters, and autonomous SAA safing, even when it trims a headline instrument's duty cycle. Build constellations so the network shrugs when one node naps over the South Atlantic. And put high-resolution magnetic updates on the same cadence as flight dynamics updates, yearly at minimum, so onboard SAA polygons match the map. Public literacy is the last mile. When people hear weakening field, they jump to flips and doom. Replace that with dashboard thinking. A handful of dials anyone can check. Mixed layer depth curves, Gulf Stream slope, coastal sea level anomalies, SAA area, and depth, and a simple storm time risk light for affected regions. If the dials turn, the actions follow. Airlines shift altitudes, grids widen margins, satellite operators lengthen blackout windows, and nobody needs a spooky headline to do it. Micro story. A control room in Sao Paulo gets the morning brief. Subpolar mixed layers ran shallow. The Gulf Stream slope stayed flat. KP is high. The SAA's eastern lobe deepened another notch. The dispatcher bumps altitudes for 2 westbound crossings. The grid operator opens one shunt, arms a special protection scheme, and delays a maintenance outage. A satellite over the South Atlantic extends its safe window by 6 minutes. By afternoon, the storm passes. Nothing breaks. The needle's bent, the people moved. That's the point. The shield is dynamic. Our job is to make its changes ordinary, watched, budgeted, and folded into work, so the South Atlantic stays a procedure, not a plot twist. Human stories in the weak spot. The ops room was quiet until it wasn't. A small Earth imaging satellite rolled into the South Atlantic Anomaly, 15 minutes early, pushed by a tiny drift in its orbit model. On screen, the star trackers snowed, the attitude loop hunted, and the gyros started shouldering more weight than they liked. Watchdog armed, someone said. A proton clipped a memory cell. The flight computer stuttered and reset cleanly. The satellite dropped into safe mode, closed its shutter, and coasted. 2 orbits later, it woke, reacquired stars over Namibia, and slipped back into its plan. In the log, the event shrank to a line. The team pushed a patch that narrowed the tracker's acceptance window during SAA passes. The next storm wrote nothing at all. A long-haul captain out of Bermulios glanced at the dispatch note taped beside the winds chart. High KP. Climb 2,000 feet between 30 west and 10 east. Expect HF flutter. The climb burned more fuel. The cabin stayed smooth. Up front, a passive dosimeter in a pocket added a sliver to a quiet tally. Over the intercom, nothing. At cruise, the first officer tried the primary frequency, shrugged at the hiss, and slid to the backup. The checklist already knew the drill. In Sao Paulo's Grid Control Center, a geomagnetic alert arrived with coffee. Magnetometers along the coast twitched first. A transformer's neutral current ticked higher. Operators eased flows on a long east-west line, pulled in another shunt reactor, and called a neighbor to trim transfers by a hair. One relay chattered on harmonics, then stayed quiet. By dawn, the plot settled. The after-action read like a grocery list. Add a JIC monitor at a coastal substation, advance oil sampling on a hot unit, drill the night crew on the next storm verb. On orbit, people wrote their own notes. A station crew crossed the anomaly 3 or 4 times a day. They joked about the South Atlantic light show. Phosphene flashes flickering behind eyelids, then logged it like everything else. Spacewalks that could dodge SAA windows did, and the dosimeters in the suit pockets told a slow story in millisieverts. The doctor on the ground tracked totals, the program tracked lifetimes, and the crew made coffee before sunrise over Angola. Far below, a loggerhead turtle swam past Fernando de Noronha, following a map stitched from smell, currents, stars, and magnetic contours that have drifted a little in one lifetime. She didn't know the phrase, South Atlantic Anomaly. She felt a coastline the way a hand feels a wall in the dark. Researchers glued a sensor to her shell and watched the line wobble, then correct, then reach the same beach her mother found. In a coastal lab in Cape Town, a team annealed a radiation-battered detector from a small satellite. 3 hours of controlled warmth turned hot pixels back to stars. The student who had babysat the procedure wrote a script to schedule anneals after storm stack passes and went home to sleep. The next morning, the images were clean. A pipeline engineer in Patagonia watched pipe-to-soil potential shift during a solar storm. "Hold rectifier steady," she told the field tech. "Walk the known holidays after lunch." A week later, they dug a patch the size of a door, measured the wall, and wrote one word in the report: intact. Across all of it ran the same rhythm: competence over drama, margins instead of miracles, a dent in the shield that keeps moving, and people who keep pace. When Swarm maps updated in 2025 and the eastern lobe deepened faster, mission planners widened blackout boxes by 6 minutes. Dispatchers added a line to the briefing. Grid operators nudged checklist forward. None of it made a headline. All of it made a difference. The shield isn't failing, it's shifting, and the South Atlantic is where we feel that shift first. If you want the next piece, the way jet streams lock cold blocks and tilt storm tracks, watch the episode queued up now. Subscribe for more untold mechanics. Drop a comment with your CA story, and share this so